Dear all, in this video I am going to discuss about a very important fluid property known as viscosity. Now, what is viscosity? Viscosity may be defined as the most important fluid property by virtue of which a fluid offers resistance to deformation under the action of a shear force. What happens when you try to move a block by pushing the block against a rough surface? You feel some amount of resistance force to move the block due to the frictional force acting between the meeting surfaces. In a similar fashion, when you apply a shear force on a fluid element and try to deform it, then the fluid element also offers a resistance force to deformation due to viscosity. Therefore, more viscous fluid offers more resistance force to deformation. In this regard, one very important law known as Newton's law of viscosity will be derived. For that, we need to consider the figure as shown. In this figure, you can see two plates. One plate is the bottom plate and the other is the top plate. Also, you can see the bottom plate is kept in stationary condition. That means the velocity of it is 0. The top plate moves with a uniform or constant velocity of magnitude caps U under the action of a shear force of magnitude caps F. The unit of caps U is meter per second if you consider SI unit system. Now, for this analysis, we consider two boundary conditions. Number 1 is the no slip boundary condition and number 2 is the no penetration boundary condition. No slip boundary condition refers that there is no relative velocity component along x direction of the fluid particles that are sticking to the bottom as well as upper plate. And no penetration boundary condition refers that there is no velocity component along y direction of the fluid particles. It tells you that no fluid can impinge into the solid boundary along y direction. Now, when we apply these two boundary conditions, we can easily say that when y is equal to 0, then u is equal to 0, and at y is equal to b, u is equal to caps u. And at the same time, we observe the deformation of fluid particles that are actually lie on a vertical line at t is equal to 0, shown by 0, 1 line in the figure. 0, 2 line represents the position occupied by the same fluid particles at some time interval let t is equal to del t. Similarly, 0, 3 and 0, 4 lines represent the position of fluid particles after t is equal to 2 del t and t is equal to 3 del t time respectively. So the maximum deformation of the fluid particles take place at y is equal to b, as the fluid particles will move with the same velocity as that of the upper plate, because we apply two boundary conditions earlier. And the minimum deformation will occur at y is equal to 0, because the fluid particles that are sticking to the bottom plate has 0 velocity, as the velocity of bottom plate is 0. The velocity of intermediate fluid particles will vary from 0 to caps u. If the gap separating between the two plates is very small, then the velocity distribution will be linear type, that is a straight line. Now, for this linear type of velocity distribution, we get a triangle PQR, where PQR is equal to 90 degree and QPR is equal to d theta by dt. Because in case of fluid, as long as the shear force acting on a fluid element, the fluid element continues to deform. Therefore, the angular deformation is considered here in red basis. Now, from right angle triangle, we can write QR by PQ is equal to tan d theta by dt, or caps U by B is equal to tan d theta by dt. If d theta is small, then tan d theta by dt is almost equal to d theta by dt. Therefore, we can write d theta by dt is equal to caps U by B, where U by B is equal to time rate of deformation and d theta by dt is equal to rate of angular deformation. Also, you can write d theta by dt is equal to U by y, where U is equal to velocity of a fluid particle at a distance of y measured from the stationary plate. Okay. So ultimately we can write d theta by dt is equal to U by B is equal to small u by y, that is equation number 1. Now, from experimental evidence, it has been established that if the shear force caps F acting on a fluid element and A is the area of the fluid element that opposes to the deformation in shape, then we can write F by A is directly proportional to the d theta by dt, or F by A is equal to mu into d theta by dt, where mu is equal to coefficient of viscosity or dynamic viscosity or simply viscosity. Also, mu is called as dynamic viscosity because in the above expression force term is included. Therefore, we can write F by A is equal to mu into d theta by dt is equal to mu into caps U by B is equal to mu into U by Y from equation number 1. Now, F by A is equal to shear stress and is generally denoted by Greek letter tau. Therefore, we can write tau is equal to mu into d theta by dt is equal to mu into caps U by B is equal to U by Y, that is equation number 2. And the differential form of equation number 2 is tau is equal to mu into du by dy, and this equation is known as the Newton's law of viscosity. Here du by dy represents the shear rate of deformation or velocity gradient, and the Newton's law of viscosity tells you that shear stress is directly proportional to the shear rate of deformation. As you can see from the velocity triangle PQR, that if any tangent is drawn at any point on the on the line PR, then the tangent represents du by dy. And for linear type of velocity distribution, as du by dy remains same, so mu also remains constant in case of Newtonian fluid. Thank you for watching my video, and if you like my video, then please subscribe my channel.